8th of August 2016. My name is Arindam Banerjee and I work for HTN Research Private Limited, a Melbourne-based research company, and this is my headquarters, so to say. Now, I would like to share with you my recent research, but for that we need to go to the 19th century, and that is why I'm putting on this cap to show you, to indicate that we are on a voyage of mystery to find out some of the deepest secrets of Mother Nature. So, what we will do is to do some electrical experiments which they could have done in the 19th century and which could have altered human destiny and taken us to the stars. Let us go and find out. Because you see, in the 19th century, they had this sense of wonderment. They wondered at how the sun was so hot. Why was there such a strong magnetic field of the sun and also the earth? How could that happen? But they did not know, but they had that curiosity. So it is with that curiosity and that open-mindedness that I request you to come with me to the 19th century and do some experiments there. Come on, let's go. Hello, now this is the picture we are getting in the 19th century, shall we say. You to note those capacitors. They were not got in the 19th century. I had to make a time machine to go to the 21st century and buy some and come back. But apart from that, everything else over there is what you could expect in the 19th century. There are two rails, there is a piece of wood on which those two rails are put, and those are on a floorboard, and they're all copper connections right to those capacitors. And there is also a small multimeter over there, which of course is also borrowed from the 21st century. Okay. Now there is no voltage across here. This is a switch, and we find that we have blocked the conductors. Now let's see how it goes. I'm letting it go. I didn't go too fast, did it? Now let's see. I'll be taking out this and shorting it now. The switch is now on. All the power is going to those two rails at 16 volts. And besides, let's see what happens. This I did go faster, didn't it? Well, we shall see how fast it went when we take a slide by slide, frame by frame analysis of the video. Shall we try again? Let us see. Now, what is the voltage here? It was 16.2, now it is 7.93. We have sent 2000 coulombs of charge over here. That's a lot. Now let's see what happens now. It won't be that much, but still. It's still a bit faster. Now it's 3.16. We have not put that much charge over here this time, so it didn't go as fast as it did earlier. Now there is no voltage across here. This is a switch, and we find that we have blocked the conductors. Now let's see how it goes. I'm letting it go. I didn't go too fast, did it? Now let's see. I'll be taking out this and shorting it now. And the switch is now on. All the power is going to those two rails at 16 volts. And besides, let's see what happens. This I did go faster, didn't it? Well, we shall see how fast it went when we take slide by slide, frame by frame analysis of the video. Shall we try again? Let us see. Now what is the voltage here? It was 16.2, now it is 7.93. We have sent 2000 coulombs of charge over here. That's a lot. Now let's see what happens now. It won't be that much, but still a bit faster. Now it's 3.16. We have not put that much charge over here at this time, so it didn't go as fast as it did earlier. So I'm holding it. Now let's see when I release it. Let's say this is the time of release. This is the time of release. Now that we can find over there, you can just see at the bottom of that screen, it is 21.76. Now that is for the non-current case. And now let's see what happens. Well, this is at the end of the rails, and here it is 22.86, right? Please note that down if you wish. And then what time does it just get out? Let's say this is the time when it gets out, and that is 23.06. All right, just note these times because they're important for us to find out whether it will move faster or not when I put the current on. Now let's see, when did I do that? Did I do it here? Now let's see, what did I do? This must have been the current case.
It did go faster, didn't it?
Okay, we'll see that whether it goes faster or not. Well, now let's see, what do I do? No, should be the other way around. Let's see. So let's take this one as the time when I release it for the current case, and it is 00.26, right? So what happens? Okay, I think this is the time. No. Okay, that is 0.01.10. That is the time to reach the end of the rails. Now to reach the end of the thing, it just hits it. But I think if we just hold this one, or let's say this one, that is. I'd say this is about the time it leaves it. So that is 0.101.26. That is the time it leaves. Now we shall compare the times for both the cases. Well, and now that we have got the values over here for the experimental results for the non-current case, and for the current case we have just got these values. Now we will do the analysis. Now what is happening is that if we subtract this, we will find that it takes 1.1 second to run down the rails for the non-current case, and for the current case it is 0.84 seconds. So the same distance is being traveled by a lesser amount of time, so that definitely means that it is moving faster. We also note that the voltage drop is from 16.35 to 7.93, which is 8.42 volts. And from there, we know from the formula that the charge is equal to the voltage drop into the capacitance. We know that 2105 coulombs have been discharged in exactly 0.84 seconds, which means that the average current is 2506 amps over the duration of the armature on the rails as it went down. So with current, we have made the speed higher, and we also know exactly what is the current. So now let's find out what is the efficiency of our motor. Okay, now it is very clear that the motor is rolling faster. So it will have more rotational energy, and because it is moving faster also, it will have a greater linear energy. Now, there are different formulas for both. For the extra rotational energy, we have half into I and omega 2 square minus omega 1 square. Now, I is the moment of inertia, and that we find out from the dimensions and the weight, and or rather the mass of the armature. It is 9.143 into 10 to the power minus 4 mks units. But the rotation speed we find from the fact that it has made 4 rotations in that period. Since in the current case it is rotating faster, we find that the difference in rotational energy is 0.017 joules. However, the motor efficiency is the linear kinetic energy due to the current divided by the electric power used in that time. Now, we find out what is the difference in the kinetic energy from finding out the velocities for the current case and the non-current case using the simple formula. And we know the time, and so we find out the acceleration, and from the time acceleration to time we find out roughly what is the exit velocity for the current case and the non-current current case here and the non-current case here. And we find from all these formulas and the results that the difference in kinetic energy is 1.39 joules. Now, what is the energy we have spent? Energy of a capacitor is half into C into V square, where V is the voltage. So the voltage before was 16.35 and later it became 7.93. So we find out that the total energy spent, the capacitor bank spent 25,554 joules. And for that it gave a kinetic energy, a linear kinetic energy due to its linear motion of 1.39 joules to the armature, and very little to the rotational energy actually. So the efficiency of our motor is 1.39 joules divided by 25,554.7 is equal to 0.0054%. Well, it is more than zero, you know. Well, what we have just seen is that if you put a lot of electrical power, you can move a heavy piece of material along 2 rails and make it get out of the system. But you may wonder, what is it all about? How can we make a motor with this that will take us to the stars? But please be patient. In subsequent videos, we will carry on with the same equipment, and then we will finally show how this can be modified into a very powerful electrical motor. You will see that.